Next we can discuss the most important concept of this chapter, that is Kirchoff's laws. So what do you mean by Kirchoff's law? Electric circuits generally consist of a number of resistors and cells, interconnected sometimes in a complicated way. So the formula we have derived for the series and parallel combination of resistors are not always sufficient to determine all the currents and potential differences in the circuit. So two rules called Kirchoff's rules are very useful for the analysis of electric circuits. Okay, and the first law stated by Kirchoff is also known as Junction Rule, and the rule is like this: at any junction, the sum of currents entering the junction is equal to the sum of currents leaving the junction. So if you consider a junction like this, and suppose some resistors are connected to this junction, and current I1 enters to this junction, current I2 enters to this junction, but current I3 and I4 is leaving the junction. Okay, so Kirchoff's law states that the total current entering the junction is equal to the total current leaving the junction. So how will you express it? So the current entering the junction can be considered as positive, and the current leaving the junction can be considered as negative. And the total current in a junction must be zero as per Kirchoff's laws. So we can write I1 plus I2, this is the total current entering the junction, minus I3 plus I4, this is the total current leaving the junction. And this is the sum of all the currents in a junction, it must be zero. So that is I1 plus I2 is equal to I3 plus I4. That is total current entering the junction. This is the total current entering the junction, I1 plus I2. It is equal to total current leaving the junction. So I3 plus I4 is the total current leaving the junction. This is Kirchoff's first rule. So let's discuss the Kirchoff's second law, my dear children. Second law is also known as the loop rule. Loop rule states that the algebraic sum of changes in potential around any closed loop involving resistors and cells in the loop is zero. So Kirchoff's law, second law, states that the total potential difference of any closed loop is zero. Okay. Algebraic sum of changes in potential around any closed loop. That means we can simply write like this: sigma delta V equal to 0. Delta V means change in potential, sigma means sum of that change in potential. So in any closed loop, the sum of this change in potential will be 0. In the figure, we have two loops. One is loop D, E, F, C. This is one loop. And another one is A, B, C, F. And we can follow this direction inside this closed loops. Okay. We can follow any direction, let it be clockwise or anti-clockwise. It's our choice. But you must move in that specified direction. Okay. Now here, suppose we are following in this direction. Consider the loop D, E, F, C. And we are moving in this direction as shown by this arrow. Now here we should know the currents flowing through each of this loop and also the EMF of the cell. So here let the EMF of first cell be E1, let the EMF of second cell be E2. And E1 provides a current I1, E2 provides a current I2. This I1 flows through the resistor R1 and this I2 flows through the resistor R2. And both I1 and I2 combine from this point. So the total current flowing through this resistor R3 is I1 plus I2. The direction of I1 and I2 is same, but the direction of I1 plus I2 is okay. Now consider the loop DEFC and just start from this point, that means from the positive terminal of the cell. So what is the current flowing through that circuit? It is I2, and when current I2 flows through the resistor R2, what is the potential drop there? It will be I2R2. So write that I2R2 is the first potential drop that we experience while going through that loop, and current flows in this direction. Then on reaching here, current is I1 plus I2, and that current I1 plus I2 flows through the resistor R3. So again there will be a potential drop. What is that potential drop? It will be current into resistor I1 plus I2 into R3. So we can write plus the second potential drop is I1 plus I2 into R3. Then again follow in this way, and finally we reach here, where to the negative terminal of the cell. And what is the EMF of that cell? E2. So E2 is also a kind of potential difference. So we can consider that as the potential difference here, and it will be minus E2. Why? Because we reached the negative terminal of the cell. So it is minus E2. And this is the total potential difference, or the sum of the changes in potential in the closed loop DEFC. And as per Kirchhoff's law, it will be equal to 0. Okay. Next, consider the loop ABCF and apply Kirchhoff's second rule to that loop ABCF. So what result will you get? Here also you must follow this direction as shown by this arrow. You must follow the clockwise direction. And here we can start from here. That means from the cell. So the current I1 flows from this cell. This I1 flows through the resistor R1. So the potential difference is I1 R1. Then we proceed in this direction, reach here, reach the point C, and then we need to move to this direction. When we move in this direction, current is flowing in the opposite direction, right? We are moving in this direction, but current I2 is coming in the opposite direction. So in such cases, we need to put a minus sign here. Okay, so that's why we use the term algebraic sum here. So we move in this direction, and when we reach the resistor R2, we see that current I2 is flowing through the resistor R2, but current I2 is coming in the opposite direction. So it will be minus I2 R2. That is the potential drop across R2. Okay. Then we reach to this cell. What is the EMF of that cell? EMF of that cell is E2, and we reached to the positive terminal of the cell. So we can write plus E2. Then after that we crossed this cell of EMF E2 and finally reached the point F. Again the loop is not closed, and from F we reached the point A, and finally we reached the point here. That means to the negative terminal of the cell. So we can write minus E1. EMF is E1 and it will be minus E1 because we have reached the negative terminal of the cell, and it will be equal to 0. Okay, so when we apply Kirchhoff's second law to the second loop, we got a result like this. So we need to study the application of Kirchhoff's law to each loop. Okay, so if we move in one direction and current is coming in the opposite direction, in such cases the potential drop can be taken as negative, as we did in the second loop. Then also if we are reaching to the negative terminal of the cell, we can consider that EMF as negative. Okay, so all these points you must remember, and you need to practice more and more problems based on Kirchhoff's laws so that it will be easy for you.